friends, in this new video we see comparison test for convergence of improper integral. Sufficient condition for the convergence of improper integral at a where f is positive in closed interval a comma b is that there exists a positive number capital M independent of lambda such that integration of f between the limit a plus lambda to b less than capital M. This is the first theorem. Now we prove this theorem. It is given that f is positive. F is positive in closed interval a comma b. Friend, we know that the improper integral a to b f dx exists if limit of this term a plus lambda to b f dx lambda tends to 0 from right exist and finite. If this limit is exist and finite, we said that the improper integral converges. Now as f is positive, the integration f from a plus lambda to b is monotonically increasing. Function is positive, so monotonically increasing as lambda decreases. For example, if we consider the example of x square is an integral, x is an increasing function, and look at this. If we take it as a 1 plus lambda to 2, then integration of this, if we take integration of this from this 1 plus lambda to b, then this will be x square divided by 2 between the limit 1 plus lambda to 2. Here what will be the value? This is 2 square, that is 4 divided by 2 minus 1 plus lambda whole square divided by 2. As lambda decreases, lambda, see this value, this is decreasing value, and whenever this subtracting value is a decreasing, obviously the subtraction will increases. Okay, so whenever the f is a monotonically increases as lambda decreases, and therefore if this integral a to b, a plus lambda to b is bounded, tends to a finite limit, if therefore is bounded, then this integration a plus b to a plus lambda to b is will converge. Okay, so whenever it this term integration in the limiting case is bounded, and it will not depend on, this bound is not depend on lambda, therefore this value a plus lambda to b, bound means whenever this value is less than m, and what is lambda? Lambda lies between 0 and b minus a. So this value of m is not depend on lambda. So whenever this term is a bounded term, obviously the integral will converge, and this will be not depend on lambda. So the whenever the point has infinite discontinuity at the left end at point a, the function whenever is bounded integral a to integral a plus lambda to b independent of the values of lambda, then the function is integrable. Present test, if we have two functions f and g be two positive functions such that f of x is less than equal to g of x, then integration of f converges if g converges, and integration of g diverges if integration of f diverges. So what is given? It is given that since f and g be positive functions, both are positive functions in closed interval a plus lambda to b, where 0 less than lambda less than b minus a, and a is the only point of infinite discontinuity. At this point we have taken infinite discontinuity, okay, in close interval a comma b. And so what is given? F of x is less than equal to g of x for all x belongs to close interval a comma b. Here we take a plus lambda to b. So what it gives me? It gives me integration of f between the limit a to b, a plus lambda to b less than equal to integration of g between the limit a plus lambda to b. Now first we consider let integration of g between the limit a plus lambda to b be convergent. If it is a convergent, then we know that it is a bounded above, that is integration of there exists a positive number, there exists a positive number such that here integration a to b and such that a plus lambda to b g dx is less than capital N, and obviously we get that integration of a plus lambda to b of f is also less than capital M by equation number 1. So that is, it means that integration of f in between the limit a to b converges. Now friend, second condition means integration of f is divergent. If it is a divergent, it is not bounded. If it is not bounded, as f is not bounded, then from equation 1 integration g is also not bounded. If it is not bounded, g is also divergent. So its proof is very easy. What is given here? Second parts, integration of f between the limit is diverges. If it diverges, that means integration a plus lambda to b of f is not bounded, above. As it is not bounded above, therefore the integration of g between the limit a plus lambda to b is also not bounded above, as it is not bounded above, therefore the integration of g between the limit a to b is divergent. So this is an first comparison test where we can compare two functions f and g. So if the relation between these two functions f and g is like f of x is less than equal to g of x, and if g of x, the greater function, is convergent, f is convergent. If the smaller function f is a divergent, then greater function g is also divergent. Second, it is called as a limit form. Whenever the two positive functions a and b defined on closed interval a comma b, and if limit of f of x divided by g of x is equal to L is a finite number, then the two functions, two integrals, integration of f and integration of g, diverge and converge together at point A. We have taken A is the only point of infinite discontinuity here. So we can see that both A and B, since f and g are positive, therefore their limit is also positive, and that means L is greater 0. So we choose epsilon greater than 0 such that L minus epsilon is greater than 0. Now it is given that limit of f divided by g between the limit is equal to L as x tends to a from right. So this implies that f of x divided by g of x minus L is less than epsilon for x belongs to the open interval a to c. So it gives me L minus epsilon is less than f of x divided by g of x is less than L plus epsilon, or L minus epsilon into g of x is less than f of x is less than L plus epsilon into g of x. Now friend, consider this L minus epsilon into g of x less than f of x. Now we can apply the first comparison test. So whenever if f of x is convergent, integration a to b converges by this equation converges, therefore integration L minus epsilon into integration of g of x between the limit a to b converges, and so as L minus epsilon is constant, integration a to b g of x into dx converges, right. And second part gives me that if g of x is divergent, okay, g of x, okay, we had firstly discussed about f of x. So we consider the second part, f of x is less than g of x into L plus epsilon, and if f of x diverges, therefore integration L plus epsilon into g of x between the limit a to b, here integration a to b diverges, this diverges by comparison test first, and so integration a to b g of x diverges. That means whenever f of x is convergent, g of x convergent, whenever f of x is divergent, g of x is divergent. Similarly we can apply the same criteria for the function g of x by considering this f of x is less than g of x into L plus epsilon. We get that whenever g of x is convergent, we have f of x is convergent. Now by considering this inequality, equation number 1, whenever g of x is divergent, f of x is also divergent. So this is about the limit form of the comparison test.